Our second type of calculation is finding an empirical formula based on some masses that have been experimentally determined. First, we would get the masses of each of the elements in a compound, and we can take those masses in grams and convert them into moles using the molar mass. We learned how to do this in Chapter 2. We take our grams, divide by the molar mass, and that gives us a number of moles. Once we have our moles, our second step is writing a preliminary empirical formula based on those number of moles, but they will probably not be in whole number form. You will likely have decimal numbers at this point. In order to get them into a whole number form, which is what we like for our chemical formulas, we're going to divide each of our numbers of moles by whichever number of moles is the smallest. And then, if necessary, we'll do a little bit of rounding to get a whole number ratio. Here's an example of calculating an empirical formula based on some masses. Someone found in the lab that they had 1.71 grams of carbon and 0.287 grams of hydrogen in their sample. We want to use those masses to find the empirical formula. First, we're going to take our grams and convert them into moles. We take our 1.71 grams of carbon and divide by the molar mass of carbon, which is 12.011, and get 0.142 moles of carbon. Then we take our 0.287 grams of hydrogen and divide by the molar mass of hydrogen, which is 1.008, and get 0.284 moles of hydrogen. That tells us the relationship between number of moles of carbon and number of moles of hydrogen in the sample. We can write this as a preliminary empirical formula. We can write it as C with the subscript of 0.142 and H with a subscript of 0.284, and that is the ratio of carbon to hydrogen. The problem is that it's not a whole number ratio. We want it to be whole numbers because we can only have whole numbers of atoms. To get it to be whole numbers, we're going to divide by whichever of the number of moles is the smallest. In this case, 0.142. We have 0.142 divided by 0.142, which gives us 1, and 0.284 divided by 0.142, which gives us 2. That means our empirical formula is CH2. A sample of hematite contains 34.97 grams of iron and 15.03 grams of oxygen. What is the empirical formula of hematite? As you approach this problem, you're going to trust that the values given in the problem are correct. Whatever ratio you come out with, you need to maintain that ratio. Be aware this is going to be a little bit tricky. Is the answer A, FeO, B, FeO2, C, Fe2O3, or D, Fe3O2? The correct answer is C, Fe2O3. First, we would convert grams of iron to moles of iron and grams of oxygen to moles of oxygen. Second, we would write a preliminary empirical formula based on number of moles. Third, we would divide number of moles by whichever of the two numbers of moles is smallest. We would end up with a ratio of 1 iron to 1.5 oxygens. Be careful, we don't want to round that 1.5 all the way up to 2, because that's not really trusting the data. Instead, we're going to multiply each of those subscripts by 2 so we can maintain that same 1.5 to 1 ratio while still having whole number subscripts. We end up with Fe2O3, which is C, instead of answer B, which we would get from rounding the 1.5 up to 2. Our third type of calculation is finding an empirical formula based on a percent composition. We're going to approach these problems basically in the exact same way as the previous ones. We just have one extra step added on at the beginning, which is changing the percent symbol into a G for grams. How does this work? We are going to assume that we have a 100 gram sample. We are basically pretending that we have 100 grams, even if we know that's not the actual mass of our sample. By making this assumption, it makes our math a lot easier. Let's say we add 100 grams of a compound containing oxygen, carbon, and hydrogen, and we found that the percent composition of oxygen in that compound was 51.41%. 51.41% of 100 grams would be 51.41 grams. If we did that same assumption for each of the elements in the compound, then our ratios should still hold true. It doesn't actually matter what the actual masses are, as long as we know the ratio of those masses. Gas has a percent composition of 27.29% carbon and 72.71% oxygen. What is the empirical formula for the gas? As you approach this problem, you're finding the empirical formula the same way you've done before. You just have one extra step at the beginning. Is the answer A, CO, B, CO2, C, C3O7, or D, C2O7? The correct answer is B, CO2. Your first step would be changing the percent symbols into G for grams. Then you'd take those grams and change them into moles. Then write your preliminary empirical formula and divide by the lowest number of moles, and round it if necessary just a little bit in order to get the true empirical formula.